In this video, we will show a proof that there is a infinitely number of prime. First, let us define prime number. A positive integer p greater than 1 is prime if it is a product of two distinct factors, 1 and itself. If the number p is not prime, then we say it is composite. The first 5 prime numbers are 2, 3, 5, 7, and 11. Let us assume that these are the only prime number, making it a finite number. So here is the proof that there are infinitely many primes. Let us assume the opposite of the statement, that there is a finite number of primes, and the only prime number are the following: 2, 3, 5, 7, and 11, with 11 as the largest prime number. And then we get the product of this prime number. Let n be the product of 2 multiplied by 3, multiplied by 5, multiplied by 7, multiplied by 11, and then we add 1 to it. Then we will have 2,310 plus 1, or that is 2,311. Now, what can we say about n? We know that it does not equal to 1 since n is greater than 1. Can we consider n as a prime number? The answer is no, because we already assume that we have all the prime number in the list: 2, 3, 5, 7, and 11. By elimination, we can say completely that n is a composite number. So 2,311 is a composite number. Since 2,311 or n is a composite number, then it must be divisible by at least one of the prime numbers on our list. So it can be divisible by 2, by 3, by 5, by 7, and 11. Now let us check the divisibility of each prime number to 2,311. Clearly, 2,311 cannot be divided by 2. 2,311 cannot be divided by 3. 2,311 cannot be divided by 5. 2,311 cannot be divided by 7. And 2,311 cannot be divided also by 11. Hence, there is no prime number in the list that can evenly divide n, which leads to a contradiction because it implies that we do not have a complete list of prime number. Again, we assume that we have a complete list of prime number 2, 3, 5, 7, and 11. And then by our proof, we have proven that we do not have a complete list of prime number. So how do we write this in formal proof? Again, we have the theorem. There are infinitely many primes. So here is the proof. Let us assume that the statement is false. That is, there are only finite number of prime. Let us assume that P1, P2, P3 up to Pn are the prime numbers. Let n be the product of this prime number, and we add 1 to it. N is clearly not divisible by any of the prime number since there is always a remainder of 1. and therefore is a composite since we assume that we all have the prime number P1, P2, P3 up to Pn. This means that at least one of the prime must divide that n evenly. However, n cannot be divided evenly by any of our primes since there is always a remainder of 1, which leads to a contradiction to our assumption that we all have the primes in the list, which implies that our primes is incomplete. The proof is complete that there exists an infinitely number of primes.